For r less than 3, and then for r greater than 3, and less than some other, this is some other number, there was a period 2 solution, which was a fixed point of f2, which is f composed with f, which is in other words f of x. If you look at f of x, that's a fixed point. Because if you start here, you apply f, you get here, you go apply f again, you go here, so it's a fixed point of f2. Right? But it's, alright. And because that comes from a sort of a bifurcation of the solution of the single fixed point. The single fixed point, it's essentially a pitchfork bifurcation. So you have the one solution, now that becomes an unstable solution, and then you have the two stable solutions, which are the period 2. So it's not exactly, so in the context of f, it's a, this is actually a dynamical, it's sort of like a hot bifurcation, if you will, because it's an oscillating solution. But, so it's like a supercritical hot bifurcation, if you will, but these are maps, not, and then what happened is you increase R more, and then there's another R critical, where, in fact, you get a 4. So you go from here to here, to here, to here, to here. And that is a fixed point of R4, which is F2 of F2 of X. Right? And what Feigenbaum discovered is that there were all these universal properties. For example, if you look at the R star n minus R star n minus 1, and compare that to R star n minus 1 minus R star n minus 2, where these bifurcations happen, and you look at the ratio, this converges when limit n goes to infinity. This converges to some number. And then the miracle was, that was good enough, that was. But if you start at it with a different map, which
will be the same.
It's the same number. And that was, and then the question is to understand at some level why that happens. All right? So the story is fairly complex. So I'm going to, so the idea is to, okay, so I'm going to start backwards rather than, I'm going to start at the end of Schrödinger's story rather than at the beginning and try to tell the story backwards.
Again?
Okay, so anyway, so Schrödinger says, let's try to implement this. All right, and the way he implements it is he's going to cheat. So that's why he can do it in elementary textbook, because it's not an elementary calculation, but he says like this. We're going to start out with the map, not this map, but essentially not this map, but a map that's just as good. We're going to write just the same map, we're just going to write it differently. We're going to write x n plus 1, so f of x, we'll call it f0 of x, is minus 1 plus mu times x plus x squared. All right, that's okay. So it's the same quadratic, so it's the same thing. This is under some shift of variables, and the point is, so this has, when mu equals 0, this is the point of the bifurcation. So the mu 0, the first critical mu, is at mu equals 0. Because what happens is that the solution at x equals 0 becomes unstable at mu equals 0. Because the minute the mu is slightly bigger than 0, this number is bigger than 1, and then x increases in magnitude. It's getting multiplied by a positive number. And so you get, what happens is then you have the two solutions. You can calculate what the two solutions are of the fixed point. Now there are two solutions of the fixed point, which are in addition to x equals 0, because we say that x equals, so we look for the p and q, and we want that f of p, f0 of p equals q, and f0 of q equals p, right? So let's write that down. We get that q equals minus 1 plus mu p plus p squared, and we get that p equals minus 1 plus mu q plus q squared. And now let's subtract these equations one from the other, and you get p minus q, or q minus p, equals 1 plus mu p minus q, right? And then you get plus p squared minus q squared, which is p plus q times p minus q, right? So let's divide by p minus q, and this gives us minus 1 here, right? So we get that p plus q equals minus 1, and then we not so it's mu minus 2. If I did that right, 2 minus mu minus 2. So minus mu plus 2. Right? Did that right? Okay, and now that we have that, we can substitute here what q is. So q is minus p minus mu plus 2, and now you got to plug this into this. You got a quadratic equation for p,
yeah,
and the solution is that p equals mu over 2 plus the square root of mu squared plus 4 mu over 2.
Plus minus.
And q, so that's this, and q is with the minus sign. Okay, so that's the p and q. Okay, so we have now found q and p. Okay. And now the point is we now start increasing, and this is valid as long as mu is bigger than 0, clearly. Because when mu is less than 0, then this thing, if mu is slightly less than 0, this thing is negative, and that's not good. So this solution is born at mu equals 0.
Wait, but now p plus q is not equals to.
Because I screwed up. I'm sure I screwed up the algebra, but
I think
that's
after that.
Let's look at the. Let's get it right.
The sum of them is mu, not minus mu, and not minus mu plus 2. It's not pretty good.
No, it's not. My printer is dead. It's not useful at all. I took the wrong papers. Unbelievable. I took the wrong papers. P plus Q is mu over 2. So I must have had gotten the sign wrong somewhere.
The first term after the equal sign.
It may be supposed to be.
Oh, yes, minus. Right. Right. That's where I made a mistake. So this would, now we get the minus 1, and now this is mu. And now life is good. So Q is mu minus P. All right, and then everything works. Okay.
Yeah.
Yeah.
It's correct now?
Yeah, no,
Yes.
Yeah. Okay. Now, so what happens now? So now we have this period 2 solution. And we can check the stability of the period 2 solution by looking at the derivative of the map at the double map, looking at F2, so we should call this F1, I guess. So we should look at the F2 prime is of P is F1 of P prime times F1 prime of Q, right? We showed that last time. And so now that we have this, we can work this out, blah, blah, blah. And what you find out is initially this is now 1 because this was -1 and this was -1, and when mu equals 0. And so starts out at 1 and then goes to 0, goes down to 0, and then becomes -1. When it becomes -1, we have our new bifurcation. And that happens at a mu critical, a mu star, which is, when you work it out, is the square root of 6 minus 2. Take my, work out the, okay.
Can you?
What happened in that?
So there's the birth. The question is when the next bifurcation happens.
Oh,
The next bifurcation happens when this is a fixed point of F2, right? P is a fixed point of F2. And now we can look at the derivative of, think about F2 as a map, right? And when its derivative is -1, that's exactly that's the sign of bifurcation. That's when it becomes unstable, because it goes from -0.999 to -1.01, and -1.01 means it's unstable because it's growing linearly. And so the instability happens at some value of mu. You work out what that is. It's square root of 6/2, which is some number, 0.4 or something or other. I had it somewhere. 0.449. Yeah. Okay. So this is the next bifurcation. So we have tracked the birth, this solution from its birth at mu equals 0 to its death at mu star. Yeah.
Can you explain why you changed the equation? I think the past it was good, no?
What?
It was good before you changed the equation. P plus Q
Is mu, because I got the sign wrong, as it was pointed out to me that I don't know how to do algebra. Okay. So now the idea is that this story now repeats itself, right? We went through one bifurcation, and now the idea is we're going to go through another bifurcation. And the idea is, so let's think about what this bifurcation looks like. What does the map look like? Not everywhere, because it's complicated. We know that F2 is complicated and F4 is even more complicated. What does F2 look like in the vicinity of P star and Q star, which is P of P of P star, which is P of mu star? What does the bifurcation look like? What does the map look like in the vicinity of P star? Because at P star, F2 is going to be becoming unstable. Just like 0, the solution 0 became unstable at mu equals 0. At mu star, the map F2 is becoming unstable, right? So the idea is let's expand it, right, around, and you do that, and you can work. Okay, and what you find is that you get the map is okay. So you have that at near, okay, so what you do is you calculate F2 of X equals P star, well actually P plus P of mu plus C. Let's expand the map around P, right? Oh, something. we're expanding, right? We want to expand the map around x equals p. But p is actually a function of mu, so that we're going to track it. And what happens is now you plug that in, and what you find is, of course, and so we want this thing, we're going to take away minus p of mu, so that this will have a fixed point at x equals 0, z equals 0. Right? Because since p is a solution, is a fixed point, it's now an unstable fixed point. Right? At the bifurcation, it's becoming an unstable fixed point, but still a fixed point of this equation. So we're going to investigate what happens. Right? So we want z equals 0 is now going to be a fixed point of this, because this thing is, so this is our new map. Right? Call this whatever, F2 twiddle of zeta is that thing. That is, this finds the new map looking when we take our magnifying glass and look in the vicinity of what happens near P. All right, and the point is that it looks like
it's 0 when z equals 0, right?
Yeah. So there's no constant piece. There's a x piece, and the x piece is something go to my office and get the printouts, because I took the wrong printouts. I have a, let me get the printout. This side.
הניסוח שלי איזה קולנוע כמה משתנים, ירדן? יצא משוואה סתומה ויצאתי סתום.
באופן סטטיסטי. סתם, קיבלתי את כל הנקודות על השני סעיפים הראשונים ובאחרון פשוט
מה כתבת שם? יצא משוואה סתומה ויצאתי סתום, ראש בגדול ויצאתי סתום. זה נראה מצחיק כל כך, הפונט שבו כתב את זה לסתום. כן, ענקי. זה משפט סתומה ויצאתי סתום. סליחה. כל טוב, כל טוב. הם יודעים איזה קולנוע בכמה משתנים? לא חושב? יש לי רעיון מרושע.
All right, so what does it look like? It looks like the following thing. It has a zeta, term linear in zeta, which is 1 minus 4 mu minus mu squared. And then it has a zeta squared term times 4 mu plus mu squared minus 3 squared and mu squared plus 4 mu. All right, and then it's got a mu zeta cubed term, and it's got a zeta the fourth term, because it's a fourth order. F2 is a fourth order polynomial.
Okay.
Right, because it's the second thing it's the second iterative of a squared of a quadratic polynomial, therefore it's a fourth order polynomial. Okay, so now the idea is that this thing, where does the square root of x this is true for any mu, right? What's special about what mu star is that this number is -1 at mu star, right? Because in fact, if you say that -1 equals 1 minus 4 mu minus mu squared, you get that mu squared plus 4 mu plus 2 equals 0, and that in fact has a solution square root of 6 minus 2. That's where the mu star comes from. All right, so fine. And now this is some ugly thing. And now what Strogatz says is there's, because if we keep the cubic and the quarter terms, we're not going to make any more progress, right? So he says we're just going to ignore those things and cross our fingers and hope that that's good enough. All right, and now, so our map now is this thing this is minus 1
Zeta is
plus...
small enough, it's good assumption, right?
What?
If zeta is small enough, it's a good assumption.
Right, yes, right. If zeta is small enough, it's a good assumption, except the problem is zeta is not really small enough, but we'll get there in a second. All right? So this is, what we're going to do is we're going to call this thing 1 minus 4 mu minus mu squared. We're going to call that minus 1 plus mu twiddle.
Okay.
Right? Because it's a number which is minus 1 at mu equals mu star. Right? And so mu star equals 0 is mu equals mu.
Yeah.
Mu twiddle equals 0 is mu
Star.
equals mu star. Right. Right? And now what we're going to do is we're going to rescale zeta by exactly that thing. Right? Then the linear term, so we get, therefore, the fixed point equation is theta divided by this ugly thing equals minus 1 plus mu minus 1 times 1 plus mu, right? Times zeta over this ugly thing, plus this ugly thing over this ugly thing, zeta squared. And so this is 1. This is, we say, we don't divide, we say that zeta twiddle is zeta divided by this ugly thing. So this is zeta twiddle, this is zeta twiddle, this is zeta twiddle. We now multiply by through, and we get that this is, because this is ugly divided by ugly squared, and now we divide it again, multiply through by the ugly thing, and we have exactly the same map that we started with.
A lot of ugly stuff.
What? Modulo the
Yes,
function.
the ugly stuff.
Yes, because we've thrown out all the ugly stuff. But now the beautiful thing is that once we did this, we can do it again. Okay, we're now sitting at the bifurcation point of F2, right, which was born at mu twiddle equals 0, right? And when is it going to go unstable? At mu twiddle equals the square root of 6 minus 2. That tells you what mu is going to go unstable because we have a definition connecting mu to mu twiddle. Right? So we know where the second bifurcation is going to happen. The next bifurcation is going to happen at mu twiddle equals the square root of 6 minus 2,
It will be a kind
which is some value of mu.
of
All right.
metric series.
What? Well, yeah, we'll get this.
That will be
Yeah, so, and now we can do it again.
Yeah.
Right? And, and every time mu, we're going to find the next bifurcation, the next bifurcation, the next bifurcation. And at some point, the claim is that there's a limit. The infinite bifurcation happens at a finite value of mu, which is where chaos sets in. That's the end of the period doubling bifurcation.
Mm-hmm.
That happens when mu, right? When this equals that. When there's no further renormalization. When mu twiddle is, right? So that is the fixed point equation. Let me make sure I got it right, but I believe I have it right. Pages 5, 386. Here, yes. Right. So the fixed point happens at when mu k equals mu squared plus 4 mu minus 2. Right. So this says that mu, right, we put this on this side and we get minus 2 plus 4 mu plus mu squared. Right? And that is the equation. And solving this, is the point where chaos sets in, supposedly, right? As
Wait, mu star equals that?
yeah, when this is, so this is, this, okay. Right, so in general, okay, so yeah, so in general, the equation is that mu k minus 1 equals mu k squared plus 4 mu k minus 2, which is the
Equals 0.
okay, because when this thing equals 0, mu, if k equals 1, this is mu 0, and then this is
K
the square root
minus 1?
minus
Wait.
2. Minus, right, mu squared plus 4 mu minus 2. Right, that's our,
No,
because of the minus.
On the left side, it's k minus 1, not plus 1.
Here, this is the mu.
David,
What?
it's supposed to be k plus 1 on the left side of the equation.
Down bottom.
Yeah, k minus 1. It's supposed to be k minus 1. Now let me
Why?
explain. Because, okay, what the mu twiddle is this. Now, so therefore, when mu is the bifurcation, the first bifurcation happened at mu equals 0. So, so when mu twiddle equals 0, right? Mu twiddle equals 0 is the next bifurcation, right? And so you set this equal to 0 to get the first, to get the second, to get what we call mu star. And now now these are mu twiddles, and here we're going to put mu. We're going to put in right. Yeah, it's confusing as all get out. So, in any case, the point is that you can go through the exercise, calculate each mu in turn. You'll see that it converges. You just play this exercise. Define every time you get a mu twiddle, find out what that is in terms of mu, and write down the fixed point equation. You'll get that in the end of the day you have some value for mu star.
But I'm not understand why mu k minus 1 is.
Well, you know that it's, so that's what I'm saying. You know it's true for k equals 1. Because mu 1 squared plus mu 1, 4 mu 1 minus 2 equals 0 is this thing. Right? So the next one is mu, now we have this thing, and this
no,
should be,
it will be mu tilde, but the other one will be mu tilde.
whatever. It doesn't matter. It's the point. It's easier to think of it just in terms of what mu gave me this mu twiddle, and now I need, in terms of mu twiddle, and
now just take the limit of k.
Right, and just right.
From
So
the
So the point, So the point is that when you do this, you iterate this game, you get a fixed point, which is that, and then now you have gotten this is the idea of renormalization. The idea of renormalization of this map of this game is that every time you want to calculate the new map, right, after always shifting to the new bifurcation point, looking at the map in the vicinity of the new bifurcation point, and it's going to look more, Now because he cheated and threw these away, it looks exactly the same every time, right? But that's not the truth, right? So what is the truth? So I went.
Exact value will be.
So I went through the exercise. Spent hours today playing with this nonsense, which is why my brain is a little mush. Where's my?
That's how we feel after Rabbi Holman.
Where is my notes? I have here. So what I did is I actually did it right. i.e. I found, okay, so this is exact up to here, but when you don't throw out this stuff, okay, you get, okay, so that the problem is you can't compute, in general, you can't compute these terms. You can only have them numerically. But what you have at the bifurcation point, you have, this is minus x plus, so this is minus c plus c squared plus 0.1647 zeta cubed minus 0.0886 zeta to the fourth. Right? So it's not exactly the same. You have, this is the size of the corrections. You see they're not terrible. Right? And they're
not the best.
Not the best, but not terrible. I had the strength to do another one. I went through the exercise again, and now at the next bifurcation, it's minus z plus z squared. This is trivial because this is sort of, the minus one is by definition that you're at the bifurcation point. This is by rescaling, so that there's no content there, right? And now the point is when you go through the exercise, now this is minus 0.0611 zeta cubed minus 0.0192 zeta to the fourth, if I did it correctly. All right? And now the hope is, I mean, now what you really need to do is to do this twice more or so and convince yourself that these things are converging and that there's, at the bifurcation point, there is some universal polynomial here, right? Which is you're going to only get in the limit when you get closer and closer to the last bifurcation point where everything, at the onset of chaos.
But we assume that every series xn that defined by a recursive that xn plus 1 equal to
this is the map, right? Well, okay. So the problem is
we'll have the same limit.
Right. Yes.
Here you look at specific
right.
functions.
So then right. So okay. So what did actually Feigenbaum do? Feigenbaum said as follows. Now that you have the sort of the idea, he says, okay, I'm not going to look at the beginning of the bifurcation at the end of the bifurcation. I'm going to look at the point in the middle, at the superstable point, where f, say 2 prime equals 0, not minus 1. All right? Then, because first of all, that happens at, for the logistic map, that happens exactly at x equals a half, because of the symmetry.
But we want to look at
okay, wait. Just wait. So initially, the thing, what does the map look like in the vicinity of x equals a half? Well, it's a parabola, right? Mm-hmm. And now, the next, when you look at the F2, it looks like this, right? And in the vicinity of a half, it still looks like a parabola, right? Upside down, but that's okay.
Yeah.
And now, then you go through the exercise again, and now it looks like, now it's again a maximum, right? Right? So it's always looking like, right? And so the idea is, he says, there's some function, universal, I'm going to claim that after infinite iterations of this game, it converges to something. And if it converges to something, what is this thing? It has the property that g squared of x rescaled by alpha equals x over alpha, I believe is the is alpha times alpha. Let me get it right. Yeah, alpha. Yeah. That if I take the map, right, the map originally looked like this. If I now take the iterative of that map, I'm going to get the same map just under a rescaling.
It's a Brownian motion, like
Right, it's a very so this is a functional equation. This is a crazy thing because it's a functional equation. It relates. It's not local at all. It relates something that happens at 1, say, to something that happens 1 over alpha. Right? So how do you solve this? You can't solve this analytically. But what you can do... what you do is you write a Taylor expansion. What he did is write a Taylor expansion for G. G is... We can define this to be 0, so it goes like minus x squared plus c1 x to the 4th plus c2 x to the 6th, so forth and so on. Right? So what he did is, okay, let's cut it off here. Right? Plug this in and make it true to
C1.
4th order. And you can find C1. All right. And then what you do is you do this, plug this in, and then you find C1 and C2. And then
like
you do this.
Theory. Right?
What?
Like perturbation.
Right. I mean, then you do this. No, it's not perturbation theory. It's numerics. Right? There's not. It's you just every time you have a horrible set of nonlinear equations to solve, and you give it to Newton or whatever Mathematica, and it solves it. And he did it 5 times, and he argues that if you look at the C1 is converging to something, and the C2 is converging to something, and the C3 is converging to something. And so he declared victory.
Wait, what?
That he claims that he can construct order by order in perturbation theory this universal function. And the point is, it's only one function like this. And therefore, all problems, it didn't matter what the initial map was, because I didn't tell you anything about the initial map. I'm just looking at the map after infinite numbers of bifurcations.
So if you define the Taylor series, you define the function.
Right. By defining the Taylor series, you define the function, and therefore, now it's really weird because this is a very strange game, but that's the game that he played. And then when he actually looked at it, these detailed calculations and compared, he saw that these things were converging to were exactly these things over here. So that was his wonderful. Now that's only half the story, because there's the other half of the story, which is how mu renormalizes. Because this is looking at the universal map after infinite numbers of bifurcations. It doesn't tell you how to get from one stage of the game to the next stage of the game, which involves mu. But that's a much harder game to play because the function is not just a function of x; it's a function of mu. And the question is, how does this function now scale change as a function of mu as well? And Strogatz says it's too complicated for him to explain, so I don't understand it.
What again?
He says it's too complicated to explain. I mean, because the mathematics involved in doing that is too hard for Strogatz to explain. So therefore, I don't know how to do it. I tried to read Feigenbaum, and it's completely impenetrable. And I guess is the Strogatz couldn't understand it either. And
so how do we know it?
Well, because he did it, and it.
Someone
it works.
Right.
Someone understands it.
Someone understands it, right? But not me. I have to admit. I've spent a few times in my life. I've spent hours upon hours trying to understand what the heck it's about. The nice thing, this game is a game you can play, right? I mean, this is a well-defined game, and you can do it with Mathematica. You can do it for 4 or 5 iterations, and see that these things are in fact converging. In fact, you could do this game not at the bifurcation point, but at the superstable bifurcation point, and see how it converges, and see that it agrees with Mr. Feigenbaum's polynomial that satisfies this recursion relation. So that is, but the point is, when he did this and showed this, everybody bowed down in awe and trembling that he actually showed that this was, there's this way of analyzing this, and you can actually do some semi-analytic game on this game. And that was the big achievement, in the ultimate achievement in chaos theory, is that he managed to analyze all these simple maps. The problem is the world is not these simple maps. I mean, you have to work very hard to find a physical system which is approximately described by these simple maps, and that's the end of this chaos story. So now, so now I just, for the fun of it, I want to talk about something, a more interesting dynamical system and more interesting bifurcations, or how which in particular I want to talk about the Turing instability. Turing is the same as the Turing machine is the same as the guy who solved the codes in World War II, broke the Enigma codes, the same Turing. The Turing test for this definition of an intelligent being and stuff like that.
It's also on the 50 pounds note.
Nowadays, yeah. Right. That's after they apologized to him for throwing him in prison for being a homosexual. And then the question is whether he committed suicide or not is still unknown, but whatever. Okay. Anyway, so this was after World War II. This is in the 1950s. He was interested in where, you look at a creature like you, or a bug or something, and it's got a pattern. It's got a very specific spatial structure to it. And the question is, how does nature do that? How does it, know to produce arms here and a head here and whatever? Or, the simple version is, you have a, a jaguar or something. It's got circles on its thing. It's got, black circles or whatever, dogs, whatever you want, stripes. Other creatures have stripes, right? A zebra has stripes. And how does nature produce these things? So, I mean, because you start out, right, like a bee or whatever, or an ant, starts out as a bunch of little cells, and at some point, a few cells decide to become the head, the others become the tail, and then on the ones in the middle, the one side becomes the front, the top side, and one becomes the back side. How does it do that? So the question was, when you're a man like that, you think deep thoughts, and he asks himself, how can nature produce patterns? That was his big question. And he said, well, it's all chemistry, because that's all there is in life. And so somehow the chemistry has to be, so we're going to write down reaction equations. All right? And so what kind of reaction diffusion equations could possibly give you a pattern? So first of all, a reaction diffusion equation is, something like you have,
diffusion.
C dot equals d squared c dx squared with some diffusion constant plus f of c. All right? So up to now we looked at c dot equals f of c. That was the whole course up till now. And now we're adding spatial dependence. And the question is there a possibility that this thing will produce a spatial pattern? A stationary spatial pattern, right? That the uniform state will be unstable, and it will instead produce this. That was the question he asked himself, and the answer is that this can't do it. All right.
You need another linear term or something.
No. You need another field. Turns out you need two fields.
And in X and Y or something
Right.
like that?
Right. Because the idea is that, let's assume that the f of c that we have, there's some fixed point of f of c. So f of c equals C star equals 0. And let's assume it's stable, because otherwise it's just going to blow up. So we're interested in a stable fixed point. So adding this term means that now we have,
You will get
right,
the
you
knowledge
have,
equation.
right, you have ck dot, right, equals f. You expand around, and so you have c equals c star plus delta c, right? You do, and now this is a function of k, right? Because this is translation invariant, and now ck delta ck dot equals, since c is a constant, c star is a constant, you have the d times d squared, the x squared of delta ck, right, plus f prime of c delta ck. Right, now by assumption, this is a negative number. All right, the solution of this is plane waves, e to the ikx, right, and therefore delta ck dot equals minus k squared plus alpha delta ck. All right, so it doesn't work, because if it's stable at all, then just putting in diffusion makes it more stable, because that's what diffusion does. Diffusion makes, if you have a bump, it wants to remove the bump. So diffusion hurts you. So making it spatial doesn't add anything, it just makes it harder to get anything interesting. Right? So that doesn't work. So he then said, well, let's imagine that there are in fact two fields.
And
So-
then you will have it because you have x, y term or something.
No. This is still one dimension. But yeah, x we're going to call u and v. So we have u dot equals du, d squared u, dx squared, plus f of u and v. And v dot equals dv, d squared v, dx squared, plus g of u and v. All right? So first of all, what happens when we don't have any spatial dependence? We want the system, again, to be stable. So we want there to be a u star v star, such that f of u star v star equals g of u star v star equals 0. Right? And we want this to be stable. Right? How do we know how to do a two-dimensional system? We have to look at the Jacobian. Right?
Mm-hmm.
And so we have J, the Jacobian is df du, df dv, dg du, dg dv. All right? And now we want this to be stable. We went through the exercise of analyzing what it takes for this thing to be stable. Right? And in particular, we need to be stable, the trace has to be negative. The only way to get this to be stable is the trace to be negative. Right? Because the trace is lambda 1 plus lambda 2, and both the lambda 1 and lambda 2 have real parts that are negative, and therefore the traces has to be negative. So at least that means that one, and the trace is df du plus dg dv,
lower than something.
right? dg dv. So this has to be less than 0. So therefore, well, at least one of them has to be negative, right?
So,
What?
there is also another solution if you will assume trace is positive.
No.
Determinate.
No. If we want it to be stable,
Okay.
this is the only way, because this is this, right?
Yes.
So therefore, one of them is negative. Let's call the most most negative, or at least the one that's negative, we're going to call that v. So v. So this term we're going to say v. We're going to choose v because I haven't told you what f and g are, because I'm doing this total generality, right? So let's say that this term is more negative than that term. This term might be positive, might be negative. This term has to be negative, right? We can redefine time to be, we can rescale time so we can set this to equal -1. right? And always, right? That's just redefining timescales. And now this thing, by rescaling the u minus u star, right? Because what this multiplies is u minus u star, v minus v star, right? Delta u, delta v. By rescaling delta u, I can also make this to be 1.
What?
And I want it to be minus 1. Right.
Why you can do this?
Because it's a linear equation. So this is delta u, this is delta v. Right? And if I rescale
Okay.
delta u by
Something
by that number,
something,
right, I can make that I think I want to make that minus 1.
Yeah, okay.
Makes my life. I think that's what I did here. So
Then you don't have another degrees of freedom.
well then, so now I only have these two numbers.
And why is negative?
What? Because again, I can rescale it by a negative number. Or what? I haven't told you whether u is bigger than u star or u is less than u star, right?
How can you be sure that none of the derivatives are 0? Then you can't rescale.
Well, okay. Well, then the system decouples, and there's a one-field problem again.
No, if one of the derivatives is 0, not both.
But then the one field is decaying to 0, and that's the only thing that's driving the other field, so that decays to 0 as well. All right. So now I have alpha and beta here, and let me just find the right page that I'm up to, because otherwise I'm going to get totally lost here. 8, 7, 6, 8, 7, 9, 10. Of course, these pages are all out of order. 5. Ah, yes. -1, -1, alpha, beta. Okay, excellent. And now, what I need to know is the determinant, right? The next thing I need to know is the determinant, because which is now very simple. The determinant is minus alpha plus is beta minus alpha. Right? Okay. And so we have the determinant is this, and alpha is greater than -1 because I said that this was the most negative of the entries.
And you also want the determinant to be small.
Okay, and now so the rescale eigenvalues now.
Wait,
You also want the determinant to be positive.
What?
Yeah.
We want the determinant to be, if they're right, because if they're both negative, we want the determinant to be positive. So therefore, beta has to be bigger than alpha, right? So beta has to be bigger than alpha, which has to be bigger
why
than
you want
-1.
Alpha to be negative?
What?
So the trace be negative.
Because if the trace, right? You're right. If this is positive and that's negative, then the determinant if this is positive, that's we want yes.
There will be negative.
So we want both lambdas to be negative, so the determinant has to be bigger than 0.
But if you rescale the matrix, why does it still need to be to whole?
Because it did. It's true. I mean.
Okay.
But you said that alpha can be either positive or negative. So
I don't know, and well, alpha has to be bigger than -1 because I assumed that this was the most negative thing.
okay.
So therefore, this is bigger than that. This has to be bigger than that.
So we still don't say anything about the sign of alpha.
No, I don't know anything yet about the sign
Okay.
of alpha. Right? So I have.
Why not bigger or equal?
All right. So then, in fact, so you get in the alpha beta plane, you have a picture that looks like this, right? There's you can work out the thing, the algebra, and you have what you have is.
Why it can be equal to -1?
Just 2 seconds. So here, this is Hopf in that regime, and this is one stable in this whole regime here. This is alpha equals 1. this is one stable, one unstable here. This is stable, complex. This is two stable, real. And this is two unstable. That's when you're working out the diagram, right? You work out what the lambdas are, the 1/2 alpha minus 1 plus minus the square root of alpha plus 1 squared minus 4 beta. So, so you get that. Okay, fine. And so we need to be, this is alpha equals 1, so for it to be stable, alpha has to be less than 1. We also need alpha less than 1, because otherwise you're either have one stable, one unstable mode, or two unstable modes, or an unstable hop bifurcation, or you have an unstable hop, and so right. So either you need alpha less than 1, because here the real part here is if alpha is less than 1, what happens? Yeah, okay, yeah. Can I understand this simply? No. Okay. Anyway, you work that out. You get that. So now, all right. So that's the conditions for that thing to have a stable fixed point. Is either we're alpha less than 1 in this region here, but above alpha. But alpha has to be less than beta. In other words, beta. This is the line alpha equals beta, so beta has to be bigger than alpha. That's okay. Now, if du equals dv equals d, if they have the same diffusion constant, what happens? Then what happens to this matrix is you have minus k squared here, minus k squared here, right? So I can, therefore, in other words, the eigenvalue lambda equals just lambda of k equals 0 minus dk squared. And therefore, since lambda k equals 0 is negative,
in some way?
What?
Degenerate in some way?
No. If they have the same diffusion, this is because I've just taken a unit matrix. So the eigenvalues are whatever the eigenvalue is multiplied by this eigenvector, and you get minus dk squared, right? So therefore, if du equals dv, again, nothing interesting happens. So we have to look at the case where du does not equal dv. And therefore, we can now choose to call, we're going to define R to be the ratio, 4, 5, yes. Yes, R, we're going to call R equals, so we're going to make this now, R is du equal over dv, which is the only dimensionless thing that, because I haven't told you how to scale length, so the length is irrelevant. So the actual value of d is irrelevant because it just defines a length scale. But the only thing that does matter is the ratio, and therefore I have minus k squared r here and minus k squared here. All right, and now, so this is my stability matrix now, which is now a function of k squared. And so the idea is that if there's going to be a bifurcation, when's the bifurcation going to happen? When the determinant is 0, right? And so I need the determinant, I'm going to need the determinant equals 0, And so here's the determinant is alpha minus k squared r times minus 1 plus k squared, right? And then plus beta. Right? If I did that correctly. Yeah. Which is when r k to the fourth minus k squared alpha minus r plus beta minus alpha. Right, so when k equals 0, I did determine was beta minus alpha. That was what we had before, and now we work out that. Okay. And now if this equals 0, all right, then we can write this as, oh, yes. If this equals 0, then yes. So when the bifurcation happens, so is when this determinant, in fact, just touches. Let's see what I want to say. Ah, yes, right. Okay. So this beta minus alpha we said has to be bigger than 0, right? And now, if we're going to get a solution of this, we need that, and r is positive, so we need that alpha has to be bigger than r, right? In order that this be negative, and then what we'll have is, in fact, something that looks like this, right? This is a function of k squared, right? Now, k squared negative is not relevant, because k squared is positive.
And why?
What?
What is it? Why?
This is the determinant. Right? And we want it to be equal to 0, right? So we can have two solutions for k squared, that's right. But when does the bifurcation start? When we only have one solution, i.e. when it looks like this. That's the bifurcation. That's the first time at which there's a instability. Right. Here, when we want to find the solution, right? If they're here, there are already two solutions, right?
Yeah,
if it's here, there are no solutions. So where the instability first sets in is here, and therefore we need that the maximum. So the discriminant has to vanish. So the discriminant is this alpha minus r squared equals 4 beta minus alpha times r.
The maxima will be at b minus b divided by 2a.
So this is the condition.
I mean alpha minus r divided by 2r.
So therefore what we get is you solve for beta. Beta is in fact alpha plus r, because you can move the 4 alpha r to here, get an alpha plus r. So it's alpha plus r squared over 4r. So this is beta critical. All right. And then the minimum, the parabola k star squared is alpha minus r over 2r. So, and now since alpha is less than 1, clearly r has to be less than 1 in order for this to be positive. So therefore, that proves to you that in fact the only time you get an instability is not only you have to have different diffusion constants, but the U field, which as we've defined it, which is the least of the two fields, least state, the U and the alpha measures the relative stability of the U field by itself, not coupled to V, to the V field itself not coupled to U. Right? They have some internal dynamics plus an interaction term. Right? These are the internal dynamics, these are the interaction terms. And so the one of the field that is least stable has to have the smaller diffusion constant. Right? And if that happens, then in fact you have an instability. So if R is sufficiently small, if beta is sufficiently big, then you can have an instability.
What is the condition now on alpha?
The condition on alpha, well, they usually give the condition on beta, so I mean you can work it out yourself. The condition on R is
To be less than that.
2 beta, the critical R, if you will, is 2 beta minus alpha minus 2 the square root of beta minus alpha. You can work that out. All right? But that's hard to see that happens to be less than 1, but it's hard to see that it's true, but you can prove that that's true.
Okay.
So the idea is that you can arrange, if R is sufficiently small and beta is sufficiently big, you can have an instability. And that instability is called, that was the point of Turing's paper, that is called a Turing instability. So you write down any set of equations, which have a stable state, right? And as long as you pick the numbers correctly, you pick the coupling constants correctly, there's a regime, and you choose R sufficiently small, you can find an instability so that this strange, which is this strange anomalous thing that you put diffusion into a problem which was stable, right? And even though normally diffusion would get rid of any structure, here it stabilizes the structure, which was a total surprise until Turing showed it. In fact, experimentally, it was amazing. This paper is like 1954, 56, something like that. It took till 1998 or something before somebody did an experiment and showed that, I mean, numerically you can do it trivially. You can do experiments. Yeah. In fact, Turing did numerical experiments himself. Because what's amazing is that the first calculation he did was actually by hand. He solved the diffusion equation. The diffusion reaction equations he solved by hand on like an 8x8 grid and just did the numbers. And then, but he also had a computer because he was Turing and invented the computer among other things. So
like Newton that invented all calculus.
Right. So and then he actually did it on a computer, but the first calculation he did was actually
wrong.
No, it was right, and just he did it by hand, which was, totally
sound hell.
Totally unbelievable. Okay, so this anyway, this is the Turing instability, and you see that it's a kind of a bifurcation, i.e., we play with the parameters, and you find that the steady state, the uniform steady state, U star equals V star equals whatever, U star equals a constant, V star, V equals V star, U equals U star. That solution becomes unstable in the presence of diffusion at this critical value of the parameters, and then you get a pattern. So the next question, the next question is, what does that pattern look like? Right? So first of all, why is there an instability? How did it happen that there's an instability? Why did diffusion help you instead of hurting you? And the answer is that okay, so you need, in fact, alpha to be greater than 0 as well. So alpha has to, so the U field has to be intrinsically unstable. So if you, just to say, excite the U field. So it starts growing. But then it interacts with the V field, and the coupling with the V field has to be strong enough to stabilize it if it's a uniform system. But if the diffusion is fast enough, what happens is, so the alpha is growing, it produces V, which is now going to tamp down, is going to back react onto U and kill it. But the diffusion, if the V diffusion is fast enough compared to the U diffusion, it can take all the stuff, the V that it's producing, get it away, and so that you can, that U can has. So this is called local excitation, global inhibition. That the U field is a local, locally unstable system, but globally the diffusion, and V is a inhibitor. It's the thing that tamps down the reaction. But if you can get rid of that and spread that out fast enough, it's not where it needs to be in order to stabilize the thing, and you get a pattern. That is the message of that. All right.
And that's why we have dynamics in nature.
Well, who knows? But that's why you have. That's why this mechanism works. Okay. And now, what's next? So let's.
Can I
Yep.
ask a question?
Sure.
What we started with? We had U dot equal D.
We had this system.
Yeah.
So we up till now we had just this, right? And that we're assuming that this system is boring, right? That everything we did up till now was saying, well, we don't want this to be boring, so we have to look for some kind of instability, some kind of bifurcation, right? Here, the UV dynamics by themselves are stable, right? They're either, gives you a spiraling into the steady state, or it goes exponentially nice, straight exponentially into the steady state. But in any case, the V star solution is perfectly stable in a uniform system. But now you put in, you have a spatial system, and if the dV is much bigger than du, in fact, the system, then if you ignite a local excitation in U, instead of the system just going back to nothing, it generates a pattern.
Okay, and also now numerically, could we, without doing all of that, like do operator splittings and then?
We'll get right. We're going to get that.
And then just do.
Well, I have to write down a specific model, right? This is a very generic model. Yeah. So in order to actually simulate it, I need, right? The problem, you can't simulate generic models. You have to simulate specific models. So the next thing on the agenda is to talk about a specific model. And then you can take that specific model, right? Take Crank-Nicholson and with operator splitting, solve this problem, simulate it, and so maybe next time I'll bring in the computer and I'll show you some pretty pictures of how this thing develops. Okay, so so we need now if we're going to simulate anything, we need a specific model. So, okay, I know that's the next thing on the agenda. Okay, yes, here we are. Okay, so the model we're going to look at that has a Turing instability for the right parameters is a model called the Brussellator. Okay, named because of Brussels. There was a guy in Brussels who won a Nobel Prize called Prigogine, and his group wrote down this model, and so it's called the Brussellator, because he was in Brussels.
What is the Nobel Prize about?
That's very hard to say.
Sounds like
it's not obvious what he. I mean, he talks a good game, but exactly what he did that was so meaningful, I really don't know. He won it in chemistry, and I think it was the first. I think it was the first model of chemical fields which did not go to because he was interested in hop bifurcations. So in fact, the Brusselator was invented to demonstrate that you could write down chemical reaction equations which have a hop instability, and they oscillate. And that was what he won the Nobel Prize for. All right. So the model is, so f of u and v is a minus b plus 1 u plus u squared v. All right. And g of u and v is bu minus u squared v. So what happens is that, okay, so you have some background production of u, right? And then...
Foxes and rabbits.
Yeah, right. So why, yeah, well, we'll see, we'll get to that. So this is a simple thing because the G means it grows, V grows, V is produced by U, and then it saturates. If V gets too big, there's some saturation here. All right, so that's a simple equation. This one's a little more complicated. So we'll get back to that in a minute. All right. So the equilibrium state is simple, right? If this is equilibrium, so what's V star? V star by this equation is, we have that B equals UV. So we have B equals UV, right? That's from this equation. So, right. And then we have to take that and plug it into here. So let's say we write V equals B over U. And then this equation says that A minus B plus 1U plus UB equals 0. Right? So that's a linear equation for U. And so now we get UB cancels the UB. And so therefore we get that U equals A. Right? So U equals A and V equals B over U, so it's B over A. That's the steady state. Okay. Now, the Jacobian, right? So Jacobian, so what's FU?
Just wait.
FU is minus B plus 1, right? Plus U2UV, right? Equals minus B plus 1 plus 2 times U is A, and V star is B over A. So that cancels. We get this is B minus 1. Right? Yes. FV is much simpler. It's U squared. It's U squared, and therefore it's B squared over A squared. And then BFGU is B minus 2UV, which is B minus 2A times B over A. So that's minus B, right? And GV is minus U squared, so it's minus B squared over A squared. All right, so here's our matrix. B minus 1, B squared over A squared.
GV is equal
isn't it
to
A squared?
minus A squared.
Yeah, and B squared over A squared is supposed to be A squared up top. You substituted V squared instead of U squared.
GV is equal to minus A squared.
Oh, this is U squared V. Yeah, so that's this is B squared. This is minus B squared over A squared, which is that times minus A squared.
That's minus A squared.
Minus A squared times B over A. Right. No, it's just minus U squared, so it's minus A squared. Right, so this is minus a squared, and this you're saying
is also a squared.
is if v is u squared is a squared. Right, and this one I hope I did right is minus b. Right, and okay. Yeah. And now, okay. So if we redefine times, did I do that right? Yeah, GB is, it says GU is B, not GUS, it says B. B minus 2, why is it G? Well, that must be a typo. Okay, a squared minus a squared, and b minus 1. Right. Okay. So when we rescale by we rescale times by a squared. So we get an a squared here, a 1 here, a minus 1 here, and this was minus b over a squared. If I. All right. Okay. And now a squared. Right, and now if I redefine let's see. And if I want to get things, if I want to rescale things right, I have to okay, so anyway, you get, so I somehow have to look at that. That doesn't make much sense what I wrote down. But, okay, so now you go through the exercise and you can write down conditions for the instability in terms of this Jacobian or whatever, or in terms of our alpha and betas, and the answer when all is said and done, once you do it, since I'm clearly not going to get the algebra right here, is that the condition is that b is less than 1 plus a squared. And the critical r, so there's a critical r, which is square root of b minus 1 over a squared. Or b critical, the b Turing is, if you will, is 1 plus a times the square root of r squared. All right. Anyway, so you can work out all that, and
what do you finally get?
Okay. So the point is that there is for r less than this number, there's a Turing instability, right?
Okay.
And so now you can and then the next thing to do is to simulate the thing. As I said, this is a reaction diffusion system, and with the nonlinear terms here, which you can do. So this you can do by Crank-Nicholson. This you can do by Runge-Kutta, simple Runge-Kutta. You do operator splitting. And then you get a simulation, and I'll show you the simulation next week, and we'll talk about what you get.
Okay.
All right.
And we will be okay.
Kessler.
Yeah.
These pages are taken from the book.
These pages were taken from the book that I tried to write about this. So we have a draft of a book.
or a draft of a chapter of a book at least.
You're writing a book to publish?
And that was the idea. We started it about 10 years ago, and it hasn't. And we got 4 chapters into it, and then like life happened, and so. But this was supposed to be chapter 1 of this book was touring instability.
Oh, a whole book about touring instability?
No. The chapter 1 was touring instabilities. And then there were other patterns.
So it's advanced book.
It was meant to be a graduate student textbook. Is what the idea was.
Could you
אפשר
upload the draft?
למצוא את הספר הזה?
What?
Could you upload the draft?
Yeah, I'll upload the draft of this chapter.
איפה אפשר למצוא את הספר הזה?
What?
איפה אפשר למצוא את הספר הזה?
על המחשב שלי. There's no fear. One day, maybe after I retire it's the end of the year, maybe that's a good thing to start working on again. All right.
That is part of your research program?